Hello APC Mechanics students in Unit 6 Oscillations, Class 2 6.1 Simple Harmonic Motion, Horizontal Oscillation, Horizontal Oscillator Part 2. Then Section 1, Position, Velocity and Acceleration of Simple Harmonic Motion. In the previous class we have seen the differential equation of a horizontal oscillator, and it is given by the following forms. All are equivalent, but they are just different representations. Now the first one is in the derivative notation, the second one is in the dot notation, and the third one is in the dot notation as well, but we're representing the angular frequency. The solution of this differential equation may be given by xm cosine omega t plus phi or xm sine omega t plus phi. And without loss of generality, let's consider the sine function solution. Now here what I meant, all of the discussion that we will do can be done either on sine or on cosine. They are perfectly the same. Now since the position function x of t is not quadratic, linear or constant, then kinematics equations for uniform and uniform varied motion break down. So remember that in kinematics, position might be constant, linear or quadratic at most. Apart from that, kinematics breakdown, we need to use calculus. And the way to proceed with velocity and acceleration is via calculus. Now what about the velocity? The velocity is related to the position via derivative. So which is derivative for sure with respect to time. Now xm is a constant, can be dragged out. And the derivative of sine omega t would be cosine, and we multiply by the inner derivative, which is omega. So the velocity in this case is given by omega xm cosine omega t plus phi, which means the velocity is variable and changing continuously. It attains its maximum value in magnitude for cosine omega t plus phi. So here, if you look at the following function carefully, so v is changing, but it's bounded due to the trigonometric function. So when does v attains its maximum velocity is when this is simply 1, because we know that cosine and sine functions have bounded values between 1 and minus 1. So for this reason, if we assume that cosine is 1, then this velocity would be the maximum velocity. And in this case, the formula for the maximum velocity is given by omega multiplied by xm. And if you think about the units, this is radians per second. Now, radians itself is not considered a unit, and that would be meters. So which gives us overall meter per second, and that should be the amplitude, which gives us the maximum velocity. Then the maximum velocity of a harmonic oscillator governed by this differential equation for the position has a maximum velocity given by Vm is omega xm. Now what about the acceleration? Acceleration is linked to the velocity via derivative. Then if you need to derive this, omega and xm are constants, they can be dragged out. Now the derivative of cosine is minus sine, and we multiply by the inner derivative, then we're gonna have omega square. So this is the acceleration as function of time, and here in this case the acceleration is also variable, it's changing with time. Then the three of the variables of motions, x, v and a, continuously changes as function of time. Now also we're interested in the maximum value of the acceleration and in magnitude. So we know that sine omega t is bounded between 1 and minus 1, and in this case we will choose minus 1 to cancel with this minus sign in order to have the magnitude. Then the maximum magnitude of the acceleration experienced by the block performing simple harmonic oscillator for a simple harmonic motion for a horizontal oscillator system is given by omega square xm. And if you think about it carefully, now the unit of omega square would be radians square per second square. Now this is not considered a unit, multiplied by meters, which is basically the unit of acceleration, which is meter per second square. Alright, then that's it, the maximum acceleration. So here the velocity is given by the following function, assuming that x is sine function. Then whether it's sine or cosine, the maximum velocity is given by that. And similarly for the acceleration, whether the position is sine or cosine, the maximum acceleration is given by that. Now how to verify that indeed xm sine omega t plus phi is a solution for the differential equation given by x double dot plus omega square x is equal to 0. So in the previous class I have demonstrated how to obtain this equation from a big law, which is Newton's second law, and I told you that, or we've put forward that this is the solution. but we didn't state from where did we get the solution. Now, one way to be convinced that this is a solution is by verification, which means that now because we have x explicitly as function of time, we can double derive x and add it with x itself multiplied by k over m and double check that indeed it vanishes. The way to verify it is to achieve the differential equation starting from the solution, so that's also another way, verification. Now we know that x double dot is a, which is given by minus omega squared xm sine omega t plus phi. Now notice carefully that this part is the position itself. So if we replace this by x, we would have x double dot equals to minus omega squared x. So let me repeat. Now I need to verify that from this we can get back to the differential equation. So we know that x double dot is the acceleration, and the acceleration is given by this format. Now notice that this is the position, which means that we have, comparing the left and the right member, that x double dot is minus omega squared x, which means x double dot plus omega squared x is equal to 0, which is basically the differential equation that we have up top, which is nothing new but the differential equation derived from Newton's second law. Then it is indeed verified. Then this, whether it's sine or cosine, perfectly work as a solution for such type of differential equations. Now section 2, a very important section given by graphical representations of variables, graphical representation of variables of motion. Without loss of generality, let's consider the sine function solution, which gives us the following velocity and acceleration. Now let's start by the position graphically. Now here on the horizontal axis we have time, and on the vertical axis we have position. Let's assume it's position for now, and I have plotted the position function. Now the equilibrium positions occur at the following points, so these are the equilibrium positions. The maximum position given by the amplitude occurs at the following points. So as you can see that just whenever we have the graph of the position, we can determine which point represents the equilibrium points, and we can directly determine the amplitudes. Now speaking about numbers, the amplitude here would be 0.5 if this is centimeters or meters. Now what about the velocity? The velocity is given by this green curve, which is omega xm cosine omega t plus phi. So here basically we're plotting the position and the velocity on the same axes. Now, okay, also let me state something before I refer to the velocity. Now remember that the curve of a sine function is something like that. It starts from 0, okay? Now also it is important to mention, in this case I'm assuming that phi is 0, okay? If phi is not 0, this curve would be shifted. Now I'm not gonna enter into the details of phi, so assume that phi is 0 and we're only interested in sine omega t. So for this reason the sine function looks something like that. Now for the velocity, it is given by a cosine function. Now why it's shifted more than the position? Because notice that the amplitude increases from xm to omega xm, and here we're assuming that, let's say that omega is greater than 1, which inflates the function. Now a cosine function looks something like that, which represents the green curve. Now maximum speed occurs at equilibrium position, which is the vanishing point. Now why these represents the maximum speed? For a very simple reason. This curve is the curve for speed, and these are the highest points. So in this case the speed is given by 1 meter per second, let's suppose, and the vanishing speed occurs momentarily at the amplitudes. So notice carefully, these are the minimum speeds, which is 0. Whenever we're talking about speed, we're talking about positive values. If we're talking about the minimum velocities, these would represent the minimum velocity. Now however, we're talking about speeds, so the minimum speeds are these 0, so they occur at the equilibrium line. But notice carefully, minimum speed, which is 0 speed, occur at the amplitude. So, and here you can start noticing some pattern regarding the harmonic oscillator that we will stress on later. Notice also, as the position decreases in magnitude, the speed increases, and vice versa, due to continuous interchange of energies between kinetic and elastic potential energy, and this also will be discussed later in details. Now the harmonic oscillator, as it oscillates, it admits two types of energy, kinetic energy and elastic potential energy. Because the mechanical energy we're assuming to be constant, when one of them increases, the other decreases. Now here, notice carefully, this represents the position. Now I'm talking about the magnitude. As the magnitude of the position increases, the speed decreases. Now let's take the second amplitude. Now here, the position is decreasing, but the speed in magnitude is increasing. If we're talking now about the sector, the position in magnitude increases, the speed in magnitude decreases. Also, if you talk about the sector, the position in magnitude decreases, whereas the speed in magnitude increases, which due to the interchange between kinetic and elastic potential energies. Now, what about the acceleration? It's being represented by the purple curve. The acceleration graph is an inverted factored function of the position with respect to the equilibrium line. Because we're assuming that phi is 0, we have a sine function that it should be similar to the red curve, but because we have a minus sign, it will be inverted and inflated or factored because we're multiplying by omega square, so it would be larger than the green and the red curves. Vanishing acceleration, zero acceleration, occurs momentarily at the equilibrium position. So at the equilibrium position, we would have zero acceleration. Why? Because the position is zero and the acceleration depends on Hooke's law, which is minus kx. So if x is 0, which means that the acceleration is 0. And maximum acceleration occurs at the amplitudes, because that would give us the maximum position producing the maximum acceleration. What are important conclusions we need to take away? When the position is maximum, the speed is 0. And this reflects the interchange between elastic and kinetic energy. So always remember, when the position is max, the velocity is min. When the position is min, the velocity is max. When the speed is maximum, the position is 0. This statement is very original, as it dictates the continuous energy exchange between kinetic and elastic potential energy, as we shall see in the coming classes. Then let me repeat and say, when position is max, velocity is 0. When velocity is max, position is 0. Now, section 3, differential equation of horizontal oscillator while friction is switched on. The aim of this section is to determine the differential equation that governs the evolution of the system for a simple harmonic oscillator in the presence of frictional forces. For that, consider a horizontal oscillator formed of a block of mass m and a spring of stiffness k. The block is connected to the spring, and the other free end of the spring is attached to a support, thus forming the horizontal oscillator. Consider a point along the motion of the oscillator between the equilibrium position and the amplitude. And let's assume that the spring is ideal, which means it's governed by Hooke's law, Hookean spring, or an ideal spring, or a linear spring even. Now, the force of the spring always points toward the equilibrium. There exists friction between the surface and the block as it oscillates. The forces acting on the block would be the pull of gravity down, the normal push up, the tension along the spring, and the friction. And basically here we're talking about kinetic friction because there is a relative motion between the two surfaces. Note that the tension always points toward the equilibrium position, and friction would be pointing in an opposite direction. And here let me say in an opposite direction to that of the motion. And I will explain more why. Now apply Newton's second law. F net is ma. So we have the pull of gravity, normal push, so the force of the spring, and the kinetic friction, which is and all of these are equal to ma. And we know that this is a vector equation. It will give the birth to two linear equations. Now we're gonna consider the projection along the horizontal, so that would be 0, 0, and we would have the following equation. And here let me state something very important, and has to deal with these signs. Now don't overthink about how the system is gonna move in order to put these pluses and minuses in front of the forces. First of all, we agreed that this minus sign is due to the indication that it's a restoring force. Now if you think about friction, ask yourself, is friction a restoring force? It's not. For this reason, friction will be preceded by a plus sign. Let me repeat and state again. Why here do we have a minus sign? Simply because the force provided by the spring is restoring force, so that would be minus. And why here we have a plus? Simply because the force of friction is not a restoring force. Now, if you consider the block at different positions with respect to the equilibrium and moving away and toward, sometimes you will notice that friction might be pointing toward the equilibrium position and away from the equilibrium position, or basically in general opposite to the direction of motion. So sometimes the force of the spring and the friction may be pointing in the same direction, and sometimes they may be pointing away, opposite to each other. Let me give you an example. Now suppose, let me say this is the point A, and that's the point B, and that's the point C, okay, and the block is moving from B to C. So because first of all the block is moving from B to C, always we have the force of the spring pointing toward the equilibrium. Because we're moving from B to C, then the friction would be also toward the equilibrium. It doesn't mean that we should place, so it doesn't mean that we should consider minus Kx and minus Ff. That's completely wrong. Okay, now let me consider another example in which that's the point A, that's the point B, and that's the point C, and now we're going from C to B. So okay, the force of the spring would be pointing toward the equilibrium, but friction would be pointing toward the right. So in this case, you can say that it's the reason because minus Kx plus Ff, because if negative is to the left, then positive is to the right, but that's not the correct reason. The correct way to think about it is to say that this is a restoring force. For this reason we have a minus sign. This is not a restoring force, so that would be plus. Since friction is opposite to the restoring force, so also that's not completely precise. We need to say it's not opposite to the restoring force, it is not a restoring force. Okay. Now, but we know that the normal push is balanced by the pull of gravity, which is mg. We can replace it. Now we have two unknowns given by x and a. We don't have any other equation to implement. Then the way to proceed is to unify x and a using calculus and promote it to be a differential equation like that. We're interested in the differential equation of x. So rearranging the terms, bringing this to the other side and reading the equation from right to left, and normalizing the second order derivative, that would be the differential equation that governs the motion of a horizontal oscillator in the presence of friction between the block and the surface, which is given by the following. And in this reason, if you want to be precise, we won't call the oscillator anymore simple harmonic oscillator, because simple sometimes refer to the fact that there is no friction. So we're gonna call it, for now, in the presence of friction, horizontal oscillator. Now, what are the interpretations? The obtained differential equation is a second order differential equation. However, the format of this differential equation is not in the form of x double dot plus omega square x is equal to 0. If you compare this equation with this format, here we don't have a 0. So we cannot use the solutions that we have obtained previously. Then the type of motion is not simple harmonic motion, and previous relations that have been determined for this motion break down. In particular, we cannot use these formulas anymore in the presence of friction, because the format of the differential equation is different. We don't have 0 anymore. We have a mu g which compensate for friction. The period and the frequency will start to decrease in value by time due to frictional forces as the oscillator loses energy in the form of thermal energy or heat. And not only the period and the frequency, but also the amplitudes. And we're talking about xm, vm, and am as well. So in the presence of friction, the period will start to increase. It will take it more time in order to oscillate, and moreover the amplitudes of oscillation will decrease. So if you plot the curve, you expect that the curve for oscillation would be something like that. And how much it will decrease, this depends on how much friction is strong. Such type of motions are known as damped oscillations. And now for the rest of the video, we're gonna solve some exercises. Exercise 1. A 5 kg object is suspended on a spring, oscillates such that its position acts as a function of time is given by the following function. Where A is given, omega is given. What is the magnitude of the maximum net force on the object during the motion? So this is straightforward. Even if you don't have much prerequisite knowledge about the oscillator, we can solve it. Now the force is given by ma, given by Newton's second law. We have the mass. Now we need to determine the acceleration. Now the acceleration can be determined from the position via double derivative. So first let me get x prime, which is the derivative of a cosine omega t. Now a is constant, it can be dragged out. The inner derivative is omega, and we multiply by minus sign because we're going to sine omega t. Now let's do another derivative, which is basically the derivative of minus a omega sine omega t. Now a and omega are constants, they can be dragged out, so minus a omega. We multiply by the inner derivative, and that would have square, and that would be cosine omega t. Now we're talking, so here the acceleration, so m is m, and the acceleration is given by minus a omega square cosine omega t. Now this is a variable, it's not constant, but since we're talking about the maximum net force, we can choose cosine omega t to be either 1 or minus 1. Let me choose it to be 1, or minus 1 to cancel with this sign, so that would be max. So ma omega square, we have the mass, which is basically 5, the amplitude is 0.8, omega is 2 to the power 2. Now plugging that on the calculator, the correct answer would be E. Also, this can be done directly if you think of F is equal to ma. Now the maximum acceleration is directly given by a omega square, and it's perfectly the same. Now an object with mass m is attached to a horizontal ideal spring with a spring constant k. The object is initially at rest at equilibrium where the position x is 0. The object is pulled to the right. Now this is very important. The initial conditions are always important, so the object is now pulled to the right. And we're assuming the positive direction is to the right. Stretched by an amplitude a. It is released and allowed to slide across a surface with negligible friction. So the direction of motion to the left, then the velocity is to the left. Which of the following is the correct expression for the velocity v of the object as function of time? So we know that the velocity is given by a omega multiplied by sine or cosine. Omega is given by square root k over m multiplied by either sine or cosine. So we can directly eliminate, that would be wrong, and that would be wrong. Now, which one would be the correct answer? At time t equal to 0, the object is at equilibrium and is moving to the left. And we know that at equilibrium, we have the maximum velocity. Now, if you replace here t by 0, that would be completely 0. But we know that at the equilibrium, we have the maximum velocity. So that's also wrong. So we're either left with A or with B. And A would be the correct answer. Why? Because at t is equal to 0, our direction of motion is to the left. And the only function that gives us a negative value, a maximum negative value, would be choice A. Choice B would be wrong. Why? Although it's give us the maximum velocity, which is a square root k over m, but that would be when the block reaches the left end, it's passing through the origin again in the positive direction. So A is the correct answer. Exercise 3. A block of mass m is on a rough horizontal surface and is attached to a spring with a spring constant k. The coefficient of kinetic friction between the surface and the block is mu. When the block is at position x is equal to 0, the spring is at its unstretched length. The block is pulled to the position x is x0 as shown above and released from rest. The block then travels to the left and passes through x is equal to 0 before coming momentarily to rest at position x is equal to minus x0 over 2. So here you notice that why initially the amplitude is x0 and it stops and changes direction at minus x0 over 2 simply because we have friction. In the absence of friction, this should perfectly reach to the other amplitude, which is minus x0. Which of the following is a differential equation that could be used to solve for the block's position x as function of time when it's moving to the left? We can directly do it. So F net is ma. On the left we have md square x by dt. On the right we have minus kx plus the force of friction, which is given by mu mg. So the correct one would be C. So that would be minus and that would be plus. A 2 kg mass connected to spring, so we have the mass, oscillates on a horizontal frictionless surface with simple harmonic motion. We have the amplitude, we have the spring constant, we need to find the period. Now the period is given by what? By 2 pi square root m over k. So we have the mass, we have the stiffness constant, we can directly determine the period. Here we have the amplitude, so this is a redundant information, and this happens in AP questions. The mass is 2 and that would be 50. Plugging that on the calculator, so just plugging 2 radical 2 over 50, because we need pi to appear as an answer, and the correct answer in this case would be 0.4 pi seconds, which is C. And finally, as an exit ticket for today's video, the following exercise. This is very important. Students in lab are attempting to determine the spring constant of a spring. They attach objects of varying masses m to the end of the spring and measure the period of oscillation for each mass object. The data for t square as a function of m, as shown on the graph, the square of the period as a function of mass, as shown. What is the approximate spring constant of the spring? Which of the following has the best fit line that can be used to find the approximate value of the spring constant, as shown? Now here they didn't mention anything about whether this is a simple harmonic oscillator, but we're gonna assume that. And the period is given by 2 pi square root m over k. Now we're plotting t square as function of m. Then let's convert the format of this equality in the form of t square as function of m. So t square would be 4 pi square m over k, and this process is known as the linearization. Now t square can be written as some number multiplied by m, which is basically t square is 4 pi square divided by k multiplied by m. Then what's the shape of this curve? What's the type of this equation? This depends on our promotion. So we're talking about y equals to ax, y is being identified by t square, and x is being identified by m. Then if we're plotting t square as a function of m, we expect that the shape of the curve would be a straight line passing through the origin, and the slope is given by 4 pi square divided by k. Now also a good approximation whenever we're calculating numbers, you can consider that pi square equals to 10 if you like, but that's not necessary. Okay. Now anyway, let's forget about this and let's proceed with the exercise. Now we know what does the slope represent. We need first, so if you look carefully, there is no problem by plotting the points. So basically I think all of these points are duplicate from this. So now we need to check whether which of these curves represents a best fit line. Now we can directly eliminate D and E, because in these two cases the best fit line, they don't passes between almost all the points or equidistant between the points, and we're left with A, B and C. And if you notice carefully, what's the difference between choices is the value of k. So what we're left is just to calculate k. Now in order to determine k, we need to determine the slope. Now let's refer to any curve, or we can in order to determine the slope. Now it's passing through the origin, so we can consider 0, 0. And let me say it's passing through this point, which is 0.5 kg. Now the units are not much important for us, and 5 seconds square. Then the slope is given by 5 minus 0 over 5 minus 0, and that, 5 minus 0 over 0.5 minus 0, and that would be 10. The units are in SI, or 10 kilogram per second square. So we know that in this case A is 10, then 10 equals to 4 pi square divided by k. Assuming that pi square is 10, or plugging it on the calculator, k would be 4 pi square divided by 10, and that would be almost 4, and the unit of k is Newton per meter, making B to be the correct answer. And that's it for me in this video, guys. See you soon in a new one.